Welcome to your tutorial on conditional probability. We're going to be focusing on the few problems in exercise 3G that were difficult. So to begin, let's begin with the few formulas we'll need here. First of all, looking at independent events, we have this formula for the intersection, or you can also say event A followed by event B. All right, so if two things happen one after another, we can find the probability of that by multiplying the probability of one by the other. That's for independent events. That means that the probability of the second one right here does not change based on the first one happening. Now for dependent events, which are conditional events, it's the same formula to find the intersection of those two events, or again, thinking of one event happening and then the next one happening, we have the same formula. You're multiplying the two probabilities, but the second probability has changed to probability of B given that A has happened, or such that A has occurred. This means basically that the probability of B changes because A has happened. So this one is different because this has happened. All right, those are dependent events. This formula, as you know, can be rearranged to solve for this portion. So if we solve for this portion, we take divided by probability of A over here and over here also. So that probability of A goes under this part. So we can see here that we have rearranged this formula into this one. So these two are the two that we're really focused on in this assignment, and they can be used to solve every problem in this assignment. Let's take a look at problem 2. All we are given is that the probability of A naught intersection B naught is 0.35, and we're given probability of A and B as well. We have to begin by finding probability of the intersection of A and B. And let's begin with the union formula. So I didn't actually mention that one in the previous slide, but the union formula pops up often as well. So here's our union formula. As you know, you add the two probabilities and subtract the intersection. Let's fill in the parts we know, because in this formula we see probability of A intersection B, which is what we need here. So if we know all these other three pieces, then we can solve for this one. I took this formula, however, and rearranged it, right? Because if we're solving for the intersection, we want this intersection to maybe be what the formula is all about right here. So I took this, moved it over there, took that, moved it to the end here, and I've just rewritten the red formula in this form with these two things swapped. Let's see what we know. Well, we know probability of A, which is here. We know probability of B, which is here. We know those two numbers, but we don't know this. So we cannot solve the intersection, which is what we need, until we know this. So let's think of this one in a different way. And we were given another clue in this problem right here, which is going to help us get this part. So think of it this way. The union, which is this part here, is actually 1 minus this, which is what we're given here. And let me show you that in a visual. So here we have a diagram where the green shaded area represents, you can barely see it here, but it's the intersection of not A, not B. And that makes sense because out here, it is neither A, it is not B, it is all the things that are not A and B. And if that's not A, not B, the intersection, and inside here is the union. You know, the two circles and everything inside them is the union. So if we want the union, we can do 1 minus this shaded part here, and then we get the leftover, which is the union. And this is the one that we're given up here. So to find the union, we just subtract the green part, which is this part, from 1. And that gives us 0.65. So now we know this union bit is 0.65. So again, this was 0.35 in green, so that means this must be 0.65 in here, which is the union. So now taking this formula again and replacing this union with the number we just found for union right here, we have all the pieces we need in order to find the intersection. Add those up, subtract that, and we get 0.2 as our intersection. So we just solved this first part. We needed the union formula, we needed this idea here about the 1 minus this portion, and then we could finish off the formula. So yeah, that is a lot going on there, but all the main ideas of probability are there. And as always pointed out, you can always just begin with the formulas we know, which is either this one or the formula for the conditional probability. So let's look at B. In B, we need the conditional probability, so we're going to write that formula that I showed you on the first slide. And to find the conditional probability of A given that B has occurred, we do the intersection and then the probability of B. So A intersection B, we already found in A, which was 0.2. Probability of B we have here. We just divide those, and that's 1/3. Now let's find this part here. Since that's a conditional probability, we can use the formula again. So the conditional probability of that is the intersection of those two things divided by this portion here, probability of that. So this number we know, again, because it's that one, 0.35. And the bottom, probability of A, is the same as 1 minus, probability of not A is the same as 1 minus probability of A, which we know is right here. So 0.35 over 1 minus 0.25, and that gives us 7/15. 7/15. All right, that was number 2. Next one, we have a number chosen at random from this list of 8 numbers. In this list, we have odd numbers, even numbers, numbers greater than 5, less than 15, all this stuff, and it's all going to pop up here. First, we're looking for probability that it is even, given that it is not a multiple of 4. So again, we see this symbol, so we know we're doing this formula here, the formula for conditional probability. So in the first one, it is even, so I'm using E for that. And then given that it is not a multiple of 4, so I'm going to put M4 for multiple of 4 and not. It is not a multiple of 4. Conditional probability here, and it's the intersection of the two things divided by the probability of the bottom part here, the last part here. So the intersection of E and multiple of 4 means which of these numbers are both, because this means and, are both even numbers and multiples of 4. So if you look at this list, multiples of 4 are like 4, 8, 12, 16, 20, 24. So which numbers in this list are multiples of 4 and even numbers? So here's our first multiple of 4. It is also even. So that's 1. Here's another multiple of 4. It is also even. And those are the only 2 numbers in the list that are both even and multiples of 4. So there's 2 out of the 8 meets this criteria. And then on the bottom of this fraction, we're going to put the multiples of 4, or sorry, the ones that are not multiples of 4. So again, 2 out of 8, which is this top part, 2 out of 8 are even and multiples of 4. And on the bottom, how many are not multiples of 4? Well, if 2 of them are multiples of 4, then the remaining 6 are not. So we have 6 out of 8. Divide those two numbers. When you divide fraction by fraction, you can cancel these two common denominators here, 8 and 8. And you're left with 2/6, which is actually 1/3. Let's look at B. In B, it says probability is less than 15. So we're going to be looking at numbers less than 15, which are these numbers here, 11 and below. And given that it is greater than 5. So I'm going to write this like this. Probability less than 15, given that it is greater than 5. So on top, we have the intersection of those two things, and on the bottom, we have probability of this part. The formula is always set up the same way, right? All right, so we have here, the intersection means things that are less than 15 and greater than 5. So what are the numbers here that are less than 15 and greater than 5? Well, if you go greater than 5, you ignore these first 3 numbers. If you go less than 15, you ignore these last 3 numbers. So the only numbers that are greater than 5 and less than 15 are these 2 right here. So that's 2 numbers out of 8. All right. So we can see we have that fraction 2 out of 8 to represent this intersection. And on the bottom, we have numbers that are greater than 5 only. So that's not counting these 3. So that means there's 5 numbers here, 5 out of 8. Again, these 2 8s cancel, and we have 2/5. Let's look at C. In C, we are looking, it is less than 5, given that it is less than 15. So here, less than 5, intersection less than 15, and on the bottom here, less than 15. So intersection of less than 5 and less than 15. So numbers that are both less than 5 and less than 15. Well, less than 15 starts here, but these are greater than 5. This is less than 5. So only these 3 numbers are both less than 5 and less than 15. So that's going to be 3 out of 8 numbers. And on the bottom, things that are less than 15, which is these 5 numbers here. So that's 5 numbers. And that becomes 3/5. Last one, D. Probability it lies between 10 and 20 here, given that it lies between 5 and 25. So between 10 and 20, given that it's also between 5 and 25. So here's the intersection, and here's the second one here. So the intersection, numbers are both between 10 and 20 and between 5 and 25. So between 10 and 20, are these numbers, and those are also between 5 and 25. So those are the only two. So we have 2 out of 8, and the numbers are between 5 and 25. So 7 through 22, that's 4 of them. And we have 1/2. Let's look at number 8. Number 8, it says a teacher gave her class an IB paper 1 and IB paper 2. 35% of the class passed both tests. So that sounds like the intersection. 52% of the class passed the first test. What percentage of those who passed the first test also passed the second test? So probability both passed, this and this happened, passing paper 1, passing paper 2 is 0.35. Probability of passing paper 1 only, which is here, 52. Now we're looking for probability, what did I write here? Yeah, the intersection, if you want to find this and this, these are dependent events because passing paper 1 also affects your probability of passing paper 2. So here I wrote out the full probability. When you have this AND event or intersection, you can multiply it, and here's a dependent or conditional probability. So to find the intersection, we do probability of passing paper 1 times the probability of passing paper 2, given that you passed paper 1. Okay. So what we know here is this number. We know that intersection, which is the 35%, both passed. We know probability of passing paper 1. We don't know the probability of passing paper 2 if you pass paper 1. And that's actually what the question's asking for. What percentage of those who passed the first test also passed the second? All right, so that's what this portion is here. It's saying those who passed the first one, how many passed the second one, given that they passed the first one. So this is what we're solving for. So all we do is rearrange this here. We divide this by this. We have that. And there's a probability of passing 2, given that you have passed paper 1, and that's what it asks for. So that's the answer. That is passing paper 2, given that paper 1 has been passed. And that's exactly what it was asking for. All right, let's look at the last one. This one is weird. Your neighbor has 2 children. You learned that he has a son, Sam. What is the probability that Sam's sibling is a brother? Okay. Oh, this is out of order. So ignore this on the bottom for a minute. The wording of the question is not great. Your first thought may be that you are being asked the following. What is the probability of a child being a son? Well, that's easy because you can have a son or daughter. So in that case, there's a 0.5 chance it will be a son, 0.5 is a daughter. So it seems like we're done. What's the chance of Sam having a brother? Well, what's the chance of that next baby being a boy or girl, whatever? It's 50%. But going further, this question is actually asking a different thing altogether. So going further, you may be thinking, is it asking what is the probability that a 2-child family is a 2-son family? In that case, we would consider the sample space. So here's all the possibilities. The family had a son-son, or a son-daughter, or a daughter-son, or a daughter-daughter. So here we can see that a 2-son family, which is right here, son-son, is one of 4 options, therefore 25%. So that seems maybe like the answer it's looking for. Like, what's the chance Sam also has a brother? Well, that's 1 out of 4 possibilities for his family. So 1 in 4 chance that Sam and his brother are the 2 kids in the family. But that's also not what it's asking. So let's look at a little bit further. What this question really is asking, so this question, however, is more than that. It is really asking, what is the probability that this family is a 2-son family? Because that's what it's saying. He has a son, Sam, and then there's another, what's the chance that he has a brother? So what is the probability this family is a 2-son family, given that it was originally a 1-son family? So the wording could have been better, but that's kind of what it's asking. So again, what's the chance it's a 2-son family, given that it was originally a 1-son family? So probability, it is a son-son family, given that originally there was 1 son. So using our formula, that becomes the intersection of those. And on the bottom, we have the probability of that one. This is a little bit tricky too, the intersection of those. But it is 1/4 because that's talking about this. Because the intersection of son-son and son is basically saying, what's the probability of a family having 1 son, which is these 3 here, but also intersection means it also must meet the condition of having 2 sons. So out of the 3 possibilities of having 1 son, there's only 1 that is a son-son. So the intersection of these 3 and this one is only this part here. That's the only overlap between these 3 and this one. So there's that 1/4, and the 3/4 is three of these four possibilities are sun. You divide those and you get your answer.